This is a right triangle and this is a wave. Do you know that this wave is generated by plotting the ratio of the opposite side over the hypotenuse of this right triangle? If I pin the vertex of this right triangle at the point of origin and rotate this other acute angle counterclockwise this way, notice that I am generating a wave that's propagating going to the right side. Similarly, if I rotate this point clockwise direction, notice that I am generating a wave that's propagating going to the left. The concept of wave is very, very important in mathematics because many real-life phenomena involve waves. For example, we have light wave, sound wave, microwave, X-ray, electromagnetic waves, tidal wave, mechanical waves like springs, to name a few. You cannot study the physics of our modern communications without a working knowledge on the mathematics of waves. And lucky enough, the sine and cosine functions that we are going to study today enable us to model mathematically and study analytically these concepts of waves. So let's begin with the main question. What is sine? The sine of an acute angle is defined in the context of a right triangle. So let's have a right triangle here. The sine is the ratio of the length of the opposite side. So let's say this is our angle alpha. The sine of alpha is the ratio of the opposite side to the length of the longest side, which we call as the hypotenuse. So with respect to this angle, this side is the opposite side, this side is the adjacent side, and this longest side is the hypotenuse. So the sine of that angle alpha is the ratio of the length of this opposite side over the length of this hypotenuse. So that is our definition of sine. For example, in this blue right triangle, if this angle is 30 degrees, and the length of this opposite side is 1 unit, and the length of the longest side is 2 units, then the sine of 30 degrees is now written this way. Sine of 30 equals 1/2. Notice that in this notation, sine is the function, and this is the function that says you get the ratio of the opposite side over the hypotenuse, and this 30 degrees is our input, and this 1/2 is the result when this input is run through the function which we call as the sine. So sine is the function that maps the angle to the ratio of the opposite side over the hypotenuse. Notice that if I have this blue right triangle with this angle to be 30 degrees, and I have another bigger triangle with the same angle measurement here at 30 degrees, notice that if I get the ratio of the opposite side here, which is 1 unit, over the hypotenuse, which is 2 units, I get a sine value of 1/2 for the sine of 30 degrees. Now, even if I extend this side and this side to form this bigger triangle, this time, this opposite side now is 2 units and the hypotenuse is 4 units, still the sine of this angle 30 degrees, which is the ratio of the opposite side, 2 units, over the hypotenuse of 4 units, which is 2 over 4, when reduced to lowest term, also give us the same value, 1/2. We can think now of superimposing those two triangles to look like this. This blue triangle superimposed over the yellow triangle, but both of them have a measurement of 30 degrees for this angle. So this opposite side over the hypotenuse is the sine of 30 degrees, which is this 1/2. If we extend this side, this opposite side, which is 2 units, over this hypotenuse, which is 4 units, is also 1/2. And that is also the sine of 30 degrees. You notice now here that as long as the angle is the same, no matter what right triangle we form by extending the length of the side and the length of the hypotenuse, still the ratio of the opposite side over the hypotenuse remain the same. That is because these two triangles are proportional. Now, mathematicians think of a clever way to find the sine of the angle. Notice that if this number at the bottom is instead 1 unit, that means we are going to think of another triangle whose hypotenuse is 1 unit, then the computation of the sine of the angle can be reduced by just getting the height of this opposite side, whatever is that height, because the denominator is 1. And in that way, most of the time when we compute for the sine of the function, we deal with this kind of triangle, which we call as a unit triangle, or in the context of a circle, we call this as a unit circle, which you have seen in our introduction when I rotate that circle clockwise or counterclockwise direction. The main point that we are emphasizing here is all we need is the angle measurement in order to find the sine value. So in the unit circle, when the length of this radius is 1 unit, then the sine function is simply the length of this vertical line, which is the height. In the ordered pair, this is the y value. But we'll talk about the unit circle later on. So this is now the sine function. The sine is the function that tells us to get the ratio of the opposite side over the hypotenuse of any right triangle, and the x here is the angle that we use as the input to the sine function. And the result here is whatever is the ratio of the opposite side over the hypotenuse. Let's examine the graph of the sine function. So the graph that you can see is the graph of y equals sine x. The x here represents the angles. So you have here 200 degrees, 400 degrees, 600 degrees, and so on. And you have here 0 degree. Going to the left are negative angles. In terms of angle measurement, when you go counterclockwise direction, the sine of the angle is positive. When you go clockwise direction, the sine of the angles are negative. Now, the graph of the sine function looks like a wave. It passes through the point of origin, and then it goes up, it goes down, it goes up, it goes down, and so on, and repeat the cycle. Now, notice that once you complete this one cycle, the next one is just a repetition of the same graph. This one is just a repetition, and then another repetition. Now, we now say that from this point up to this point comprise one period of the sine function. And that one period is 360 degrees. Or in terms of radian measurement, that is 2 pi. Now, you might be asking, why 2 pi? Remember that when you have a circle, and when we let the radius of this circle to be 1 unit, then what is the circumference of the circle? The circumference of the circle is computed by the formula 2 pi times the radius. Now, since the radius is 1 unit, then the circumference of a unit circle is 2 pi. In other words, if I put a string around this unit circle and I stretch it like this, the length of that string that go around the circle would be 2 times pi, or 6.28, or 2 times 3.14. So that is now the reason why one complete rotation around the circle in degree is 360 degrees, but in radian is 2 times pi, where pi is 3.1416 approximately. So in this graph, one period is 360 degrees in degree measurement, or 2 pi in radian measurement. Now let's explore the graph of the sine function using desmos.com. So I have here the transformation form of the sine function. It is y equals a times sine of the quantity b times the quantity x minus c plus d. So what are all these letters referring to? So let's take a look first at the effect of a to the graph. So the a is this value. If I'm going to increase the value of a, notice what happens to the graph. The graph gets taller and taller. If I decrease the value of a, the graph becomes flatter and flatter. And then if a becomes negative, the graph is reflected with respect to the x-axis. It's like a mirror image. And then as the absolute value of a becomes bigger and bigger, the height of the graph becomes taller and taller. So that's the effect of the value of a to the graph. Now, what happens when we change the b here? The b is here. If I change the b, notice what happens to the graph. The graph is like a spring that's being squeezed. And then when you decrease the value of b, it's like a spring that's being released. So b is bigger, it's being squeezed. And then when I decrease the value of b, it's similar to a spring that's being released. So that's the effect of the b in the graph. Now what happens if we change the value of c? C is this number. I move to the right. You can see that the graph is moving slowly left and right. So in other words, this c affects what we call as the horizontal shift or the phase shift of the graph. What happens if I change the value of d? So let's look at the graph. If I change the value of d from 0, change it to 2, it goes up, change it to 3, goes up, change it to 5, it's now above. If I make it negative, minus 1, the graph goes down, minus 2, minus 3, minus 4, minus 5, and so on. So the effect of this D is to displace or translate the graph up or down. You just have to slide up or down the graph. So let's summarize all these observations. So we said that the transformational graph of the sine function is in the form A times sine times the quantity B times the quantity x minus c plus d. So we said that this is the transformational form of the sine function. Because by using this transformation, we'll be able to find what is the height of the wave. We'll be able to know how many cycles per period are there in the graph. We will know whether the graph is translated to the right or to the left. And we'll be able to know also if the graph is translated up or down. So let's begin with the vertical shift. If there's a number that's added to the sine of x, for example, from sine x, which is this red graph, and we added 2, which is now the graph that is light blue here, the graph is still the same waveform, only that it is displaced or it is moved up or it is translated or slide up 2 units. So that is the meaning of the vertical shift. It shows how far the function is shifted vertically from the usual position. And in our formula, think of that as the value d, as this d in the formula. Next is the horizontal shift. The horizontal shift is this letter C. So for the horizontal shift, notice that the number is added inside the parenthesis. That becomes the input to the sine function. So when you have sine of x, the graph is this red graph. If I added 90 degrees to x, the graph from this red graph is pushed to the left 90 degrees. Notice that when you have the plus sign here, the graph is instead moved to the left, contrary to our expectation that the graph should be moved to the right. So the sign here is opposite. When you have plus 90, the graph is going to the left by as much as whatever is the value that you have added here. That value is the C in our formula. And that represents what we call as the phase shift, which is how far the function is shifted horizontally from the usual position. If instead of adding 90, we subtract 90, notice that from the red graph, the blue graph is the same shape, only shifted 90 degrees to the right. So think of the red graph that is being pushed to the right 90 degrees. And everything, the shape and height of the graph are just the same. It's only shifted to the right when you have a minus sign here. So that is what we mean by the phase shift. Now the next thing that we're going to explore is the value A. Notice that in our equation, A is this value. What is the effect of this value to the graph? Let's take a look at this. From the mother function y equals sine of x, which is this red graph, if we multiply the function by 2, as represented by this constant 2 times the sine of x, notice that the height of the graph becomes 2. When I say the height is from the midline of the wave going to the peak. The peak is this, and this length is 2 units, and that is the same as this number 2. And on the other side, you also have negative 2 going down here. So therefore, whatever is the absolute value of A, that represents the distance from the midline of the wave going to the highest point. So the distance from here going to this lowest point is twice the absolute value of A. Or from this point going to the midline is this value A. Now, if the sign of this A is changed from positive 2 to negative 2, the effect of that would be to reflect the graph vertically. That means this point is reflected to the other side, this point is reflected to the other side, so the new graph would look like this. So we call that as vertical reflection. It's like you rotate this to go to the bottom, in this bottom you rotate to go to the top. Now the amplitude is the height from the center line to the peak. Or we can measure the height from the highest to the lowest point and divide by 2. So the amplitude or the height of this function is 2 units. And you can detect that by just looking at this number that is multiplied to the sine function. In here, notice that I multiplied the sine function by 3. Notice now that the height is 3 units. From the center line to the highest point is 3 units. And if you're going to combine now all these different changes in the amplitude, the graph of y equals sine x is this red graph at the middle. The graph of y equals 3 sine x is this graph that's the tallest. The graph of y equals 2 sine x is this blue graph. And when we change the sign from positive 2 to negative 2, we reflected this blue graph to appear like this green graph. Those are the effect of changing the value of a in our equation. Now, a while ago, I said that the period of the sine function is the length in the x-axis in order for us to complete one cycle. So the wave that I trace green is one cycle, because after this point, it's just a repetition of the same shape. In other words, the wave is composed of a lot of cycles. And this one cycle is 2 pi. And that is the period of y equals sine x. But this period will be affected if there is a number that is inserted between the sine and this x. Now, what is the effect of this number that is inserted between the sine function and the variable x? Instead of having sine x, we now have here sine of 2x. And this 2 is the letter b in our formula. Now, let's look first at the red graph. So from here, from this point to that point, we have 360 degrees. 360 degrees is the period of the sine function. Now, if you have sine of 2x, the graph of that would be this blue function. Notice now that if you are going to trace the blue graph from here going to this point, going to this, that is one cycle. And then let's repeat that cycle now here. And from here going to that point is another cycle. In other words, from this point going to this point, we now have 2 cycles. We now have 2 cycles in the span of 360 degrees. In other words, we can find the number of cycles of the graph y equals sine of 2x by using this formula. 360 divided by whatever is this number, divided by 2, we will get 360 divided by 2, 180. This 180 becomes now the period of this new function. So the period now is the length in the x-axis to complete one cycle. And the function y equals sine 2x has a period of 360 divided by this 2, which is 180 degrees. And you can now think of this number 2 as the number of cycles in 360 degrees, or 2 pi. So from the period from 0 to 360, there would be 1, 2 cycles. Or another way of naming this 2 is we call that as the frequency. Notice that in your radio station, we have what we call as the frequency of the FM station, or the frequency of the AM station. That refers to this number of cycles per unit of time. So if you now have y equals sine 3 times x, from here, we can know that the period of this graph would be 360 divided by 3, which is 120 degrees. So from here to 120 degrees, that comprises one cycle. And that is the period. The period is the length in the x-axis in order for the wave to complete one cycle. And the number of cycles from 0 to 360, the period from 0 to 360, this is 360, not this one. So from 0 to 360, there would be 3 cycles. Let's verify that there are 3 cycles. So you have 1, you have 2, and you have 3 cycles. So by looking at this graph, you know that this 3 represents the number of cycles for every 360 degrees. And 360 divided by this number would be the period. And the period is the length for the wave to complete one cycle. So putting them all together now, if you have y equals sine 6x, notice now that this 6 means that we will have 6 cycles in the period from 0 to 360. And we can verify that. 360 is this point. Let's count the number of cycles. You have 1, you have 2, you have 3, you have 4, you have 5, and you have 6. And what is now the period of sine 6x? The period is 360 divided by 6, which is equal to 60. And 60 is this point. So the period is 60 degrees. That is the length in the x coordinate for the wave to complete one cycle. And here's the definition. Frequency is the number of cycles it completes in a given interval. So in a given interval, let's say from 0 to 360, we have 6 cycles, and therefore we now say that the frequency here is 6. In the sine function, that interval is generally 2 pi radians or 360 degrees. So to generalize that observation, we now define period as 2 pi over b, or in degree measure 360 over b. This gives us the period of the sine function. So to summarize all our observation, whenever we are graphing a sine function, we want to transform it so that it looks like this, where this a represents the height of the graph. So the height is this height. This b represents the number of cycles in 360 degrees. This c represents whether you move the graph to the left or move the graph at the right without changing the shape of the graph. And this d represents the vertical shift. Either you move the graph or you slide it down without changing the shape of the graph. For the terms, we call this a as the amplitude. We call 2 pi over b as the period. This d is what we call as the displacement or the vertical shift. And this c is what we call as the horizontal shift or the phase shift. So those are some of the properties of a wave that we can study analytically. So let's apply what we learned so far. If you are given the function f of x equals 2 sine of x plus 45 plus 1, what can we deduce from this form? We know that the amplitude is the absolute value of a, and the absolute value of a here is the absolute value of 2, which is 2. So we know that the height of the wave is 2 units. Now, what does this plus 45 means? We said that if this is plus, the graph is going to the left. So that means there is a phase shift of 45 degrees to the left. This one is the vertical shift that is positive. That means the graph is moving up 1 unit compared to the graph of the mother function, y equals sine of x. Now the period is 2 pi over b, or 360 over b. But there is no number b here. So that means b is implied to be 1. So that means you have 360 over 1 equals 360. That is the period, 360. And let's now sketch the graph. In the graph, looks like this now. The red graph is the graph of y equals sine of x, and the blue graph is the graph of this formula. Notice now that the graph is push 1 unit up. It's push 1 unit up, it's towards the upper part, and the graph is shifted a little bit to the left, which is this 45 degrees, and the period from this point to complete one cycle is to see the same positioning here. Like, I started a little bit going up, I will end at the same position, a little bit going up. So what is now the length of this in the x-axis? That length is the 360 degrees, which is the period that we have just computed in the previous slide. The graph is translated a little bit up by 1 unit, and the graph is translated a little bit to the left by 45 degrees. And the graph is stretched vertically to have a height of 2 units compared to the graph of y equals sine x. So at this point, we are now ready to answer our math problem of the day. The problem that was given was, the height of water in a wave pool oscillates between a maximum of 13 feet, so this is 13 feet, and a minimum of 5 feet, this is 5 feet. The wave generator pumps 6 waves per minute, so 6 waves per minute. If there are 6 waves per minute, that is equivalent to having 6 waves per 60 seconds, or 1 wave for every 10 seconds. So we need to remember this. The graph of the sine function is in the form f of x or y equals a sine b x. Let's determine what is a. So the midline here is at 9. The length from here going to the highest point is 13 minus 9, which is 4. From this point going to the lowest point 5 is also 4 units. So that means our a is 4. Notice that the graph should be centered at the point of origin, but now the center is at this point. And what is that displacement? That is 9 units up. So our d is positive 9. Notice that the center point is still at the middle, so there is no horizontal displacement. So that means our c is equal to 0. Now, how do we determine the b? We said that the period of the graph is 2 pi over the b. That is equal to the period. Or similarly, we have 2 pi over the period is equal to the b. But a while ago, we said that there is one wave for every 10 seconds. So it takes 10 seconds to complete one cycle. That means our period is 10 seconds. So using now this formula, we will have 2 pi over a period of 10 seconds. That would be equal to our b. And that is 2 pi divided by 10. We can cancel out the 2. So 2 divided by 2 is 1. 10 divided by 2 is 5. Our b, therefore, is equal to pi, 1 times pi is pi, over 5. So the number that we are going to substitute for b is pi over 5. So that means now that the graph as described in this problem is in the form y equals, our a is 4, copy the sine function, our b is pi over 5 times x, our c is 0, so we don't have to write that anymore, plus our d is 9. When you graph this sine function, you will notice that you will get this graph. So that's how we solve our math problem of the day that involve transformation of the sine functions.